All right, guys, so welcome back. This is our first video for week 6. We're going to have two. We're going to break it up into a video with systems and Atwood machines, which are just specialized systems. And then we'll talk about inclines, which is a different approach to a different type of problem. So jumping right in, lots of times in situations that we're going to encounter, there are multiple objects and they're all accelerating together. So this example of like a train, so if there's a train and it's pulling all these cars behind it, each of these things are all kind of moving together. This is the situation that we're going to start with, which is like there's several boxes being all pushed together at once. This is our Atwood machine. So we often treat them as a system. So the system means that we're going to select the things that we care about, and we're going to basically just treat them as one big object. And then we're going to solve for the acceleration of just that one big object, and then we'll take them and separate them into their pieces with that acceleration and the other information that we know, and solve for their individual forces that are acting on them. We're going to talk about what's called external and internal. So external would be anything that is outside of your system, and then internal would be those forces that are within your system. So if we're talking about this train car real quick, let me circle it. I put a red circle around the train cars, which are going to be our system. And then these like forces that are in the circle, we can't really do anything with those. We can just worry about the forces on the outside. So this train pulling would be the force that's acting on these three cars together, which is our system. But once we get that acceleration from those, the work that we're going to do, we're going to be able to solve for what are these individual forces of these like coupled cars together that are pulling on each other. Same idea with here, like what are the forces of these boxes pushing on each other. So we kind of simplify it down to one big object, and then we separate it into its pieces. So the first one, I've kind of worked through this problem, and so I'm going to talk through it kind of slow and make sure that you understand it. So I'll read the problem first. So force of magnitude 7.50 newtons pushes three boxes with masses M1, M2, and M3 that are shown in this picture. It says find the contact force between box 1 and 2, and then the contact force between 2 and 3. So we're really looking for like, what are these, how much are these boxes pushing on each other? And if we tried to do this right away, we wouldn't have enough information. So what we're going to do is we're going to kind of group all these boxes and just imagine it's one big box. So instead of having it as three separate boxes, I just formed this super box over here. And this force on the outside F, which is 7.5, is pushing on that group of boxes together. When you combine things together, you need to figure out their total mass. So I combined the mass together by adding these three numbers, and I got 9.4 kilograms. Again, just like most of our force problems, we start with a free body diagram. So we treat it as a system. So this is our system. Our force F is outside that system. There are other forces that are outside of that system. There are the forces that we normally think about. So gravity is trying to pull all these boxes downward, but the normal force of each of the floor pushing up on each one of these is preventing that from happening. So those are balanced. And in these cases, in this case particular, and the next one that we're going to do, sometimes you can just not worry about those forces because they're not having any impact on the acceleration. So in this one, the vertical forces cancel in all the cases on box 1, on box 2, and box 3. The gravity and the normal force are all canceling. So we're just going to worry about the horizontal or left or right forces. So when we do that, there's only one force that's really acting to make up the net force. So the net force, again, sigma F, this is sigma, this Greek letter here that I'm drawing again. That means add. So you're adding up all the forces on 1, 2, and 3. The up and down forces cancel. So all we have to worry about is this force F. And I have this force F going to the left, so it's negative. So I have the sum of the forces, or the net force, is equal to negative F. And then with Newton's second law, we can just say it's equal to MA. Notice I put in the subscripts. So this is the forces on all of the boxes at once, our system. You could write system here, but I just write 1, 2, 3. And that would be the mass of 1, 2, 3, and that would get us their acceleration of everything together. So if we plug into this, it's pretty simple. Newton's law, second law problem. So it's negative 7.5 equals the total mass, which is 9.4, equals the acceleration of our system. We divide through by the mass of our system, and we would get our acceleration. So this whole thing, this big group of boxes together, accelerates at negative 0.798 meters per second squared. Negative meaning it's going to the left. Okay, so that is our acceleration of our system. And then now we're going to approach it as an individual thing, because really we didn't want the individual or we didn't want the total acceleration of the system. We need it to be able to solve for are forces of interaction between the boxes, but it didn't ask for that directly. So, but because everything is kind of connected or pushing on each other and it's working together, so it all slides together. So if you imagine I start pushing on the edge of a box and they're all pushing against each other, this one box isn't going to like shoot off in front or faster than the others. So the acceleration of the system is equal to the acceleration of each individual piece, which is where that becomes useful. So then we can now isolate for individual blocks, and we basically do the same thing. We draw a free body diagram, we figure out our force equation from the free body diagram, and then we solve for whatever is missing. So we have 3 boxes here. I've highlighted them in different colors. So we have the red box, which I put a red dot for, the blue box, which is box 2, which is the blue dot, and the purple box, which is box 3, which is over here. And I drew the individual free body diagrams for each one. So for each one, they have normal force and gravity, the vertical forces, so up and down forces. Again, we said in the beginning, these forces aren't going to do anything to change our acceleration in this problem because there's no friction, so we don't really have to worry about them. So they're just canceling out. So I drew them in. Notice I drew them differently because we have different masses. So as the heaviest or biggest mass has the largest arrows for the force of gravity and the normal force. So anyway, I just drew the forces that were acting. So this green arrows here are acting between 1 and 2. So if this is box 1 in red, the force is coming from 2 on 1. And then for box 2, there's a green arrow going to the right because the box 1 pushes back on box 2, so a force of 1 on 2. And then 3 is pushing on 2, so that's the blue arrows that I have there. And then finally for 3, just this individual purple box, I have this force from the outside, which is 7.5 going to the left, and then the force of 2 on 3 going to the right. It doesn't really matter where you start solving. You just have to solve and set up an equation. I usually pick the easiest one. So this looks like the easiest one. I would say it's easiest because it's simplest. It has the fewest forces. So this, you don't worry about the up and down ones here, but these have 2 and these have 2 and this has 1. So 1 is easier to solve for than 2. So if we start with box 1, which is what I started up here, then all we have is the sum of the forces on box 1, or the net force on 1, is equal to 2 pushing on 1. And I can set that equal to, again, Newton's second law, all the net force is always equal to the mass times the acceleration. Again, be careful with using the right mass for the situation. So it goes along with this free body diagram, which is going on with the 1.3. So the force of 2 on 1 is equal to 1.3 times that acceleration that we got on the last slide, which was negative 7.98 meters per second squared. We multiply them out and we get negative 1.039 newtons. That should make sense because this box is getting pushed to the left, so the net force has to go to the left. The next force that I picked, and it doesn't really matter, I don't think setup 2 or setup 3 is significantly harder than the other, but I already knew this force, and I just got this answer of 1 on 2. So like you have enough information in both of these, but I'm looking for 2 on 3. So I just picked this one. So in case I mess this number up, this should still work. So for situation 3 or box 3, the sum of the forces on 3, the net force on 3 is equal to negative F, because that force is going to the left, so that's why it's negative, plus a positive F2 on 3. And again, this whole thing, this whole system, boxes 1, 2, and 3 all accelerate to the left. So that means that this force F is bigger than the force of 2 on 3. And again, the net force is always equal to M times A. So you always just like sum up your forces and then set it equal to MA. So this mass in this box or this picture is box 3. So negative 7.5 plus the force of 2 on 3, which is what we're looking for, is equal to 4.9, because that's this mass, times that acceleration again, which is negative 0.798. We're going to keep going and solve. So you would do that math in your calculator and then add 7.5 to it, and you get a force of 2 on 3 of 3.59 newtons. If you wanted to check it, you put 3.59 newtons here, and it's negative, and you put the negative or 1.039 here, and it's going to the right. And the difference in those two is the net force, and you can divide it by this 3.2, and you will get the same acceleration of negative 0.798. That is the way that this works. So that is how you deal with like forces within situations. So you have the whole system. You treat all of the objects together as one big system that works together. You find the acceleration, then you break it up into pieces, and you basically repeat the process, drawing free body diagrams, setting up your force equations with the sum of the forces that are equal to whatever the forces are in your picture, equal to M times A, you solve for the missing force and you keep going until you get everything. Okay, so let's try one problem together and see how we're going to do. So it says a train engine pulls a train with 3 cars. Each car has the mass shown. Suppose the cars are connected by metal bars with tensions indicated in the diagram. The engine accelerates at a rate of 2 meters per second squared, and we want to assume that it's all frictionless. So we're going to try to figure out, and I'll move these down so you can see the picture a little bit better. What are these forces like F2, F3, and F1? So the thing with systems is you pick what's in your system. So I just put the train cars in the system. So I picked A, B, and C. If I circled everything here, then I wouldn't know anything. I would just know this whole thing accelerates at 2 meters per second squared, but I wouldn't know why. So I'm going to pick A, B, and C, which are the train cars to the left of the actual train engine itself, and call that the system. So F2 and F3, those are internal forces. They are inside of my circle that represents my system. F1 is outside of the circle. So that's like the force that's propelling it forward. It's sort of like in the last problem, it would sort of be like the force on the outside pushing the whole thing. So this time it's just F1 is pulling this whole thing. So if we look at this, and this was hard to read, so I traced it again. So that's like 3,000 kilograms, 2,000 kilograms, and 1,000 kilograms. So if I add all those together, so the mass of the system would be 6,000 kilograms because 1 plus 2 plus 3 is 6,000. And then we're going to draw our free body diagram. So again, it's not overly complicated. When you draw the free body diagram, in this situation, again, the up and down forces are canceling out. So I had it as A, B, and C. So the normal force of A, B, and C is equal to the gravity force of A, B, and C. So they're just canceling out. And the only force we have acting is F1. So we have this force going to the right, and we need to figure out how big it is. So we know the mass of the cars, and we know the acceleration of the cars. So it's just a simple Newton's first law problem. So we're going to take the sum of the forces on ABC, which is just equal to F1, and that's equal to the mass of all the cars together times the acceleration. So the mass of the total, all the cars is 6,000 times 2, so that's going to be 12,000 newtons. So 12,000 newtons is what F1 is. So we figured out F1. Again, we're going to draw free body diagrams. Just looking at these again, you figure out forces that are pulling. This is really similar to the other problem that was just pushing before. The one that's going to be simplest is C because it just has this F3 pulling to the right. Car B has F3 and F2, so that's more forces, so that's harder. And then car A has F1, which we know, so that's a little bit easier now. And then F2, which we don't know, so it has 2 forces again. So I'm going to start with C. So if I just focus on C and draw the free body diagram for that, for this red dot, we have gravity on C, that's supposed to be a C pulling down, the normal force on C pushing up. Again, they're balancing out. We don't really care about them, but I always draw them in just to make sure we're still thinking about them the right way. And eventually, in sort of the next problem, or one of the problems we're going to do, it does have an impact, so you have to worry about it. And F3 is the force that is accelerating it. That's the net force. So if we keep going, some of the forces on C is just 1. It's a positive F3, and that's equal to the mass of C times the acceleration. The mass of C is 3,000. The acceleration is 2. So 3 times 2 just gets you 6,000. So again, not overly complicated, but you just have to be able to work through and kind of collect the objects together in your system and use it appropriately. Finally, you could pick A or B for the end. Again, whatever one you solve for, you can use the last one to check it. I did A. So looking at A, these are my forces on A. So again, up and down gravity forces aren't doing anything because there's no friction in this problem. F1, which we said was 12,000, that's pulling to the right. So that's the bigger force because the whole thing accelerates to the right. And then F2, this other tension in this coupling is going the opposite way. So again, that's our forces. We have basically a positive F1 and a negative F2. So if we keep working it out, the forces on A, positive F1, negative F2, it's just looking at your picture. It tells you what your equation is. So this part of the formula just comes from that picture. And we set it equal to MA all the time. So the sum of the forces, the net force, is equal to MA. This is MA, mass of the A car times the acceleration. So we plug into that, we got 12,000. Let me just delete the rest. 12,000 plus a negative F2 equals 1,000 times 2. So we got 12,000 plus some negative number equals 2,000. So this is going to be 10,000. So 10,000 newtons is F2. Again, a real way, quick way you can check So if you do, okay, this is F2, we said was 10,000. If we're talking about this car here for B, so we got 10,000 going to the right. We said F3 was 6,000 going to the left. So if I had those two forces counteracting each other, 10,000 minus 6,000, I have a positive 4,000 for the net force. And then the mass of the car, this car here that I put the X on, car B, is 2,000. So 4,000 divided by 2,000 leaves you 2 for the acceleration. So 2 meters per second squared, which is what we said all of the cars were accelerating at. So the only way that will work out properly is if you did everything right. So like if you wanted to check it with the last car, you could. All right. So we're going to keep going with the systems approach, but we're going to apply it to what's called an Atwood machine. So this is an Atwood machine over here. An Atwood machine is basically a pulley with a string over top, and that string is connected to 2 blocks. So we have 2 blocks here. We're going to do an experiment in class and work through some ideas in class that deal with Atwood machines. So that might be helpful. We'll do a demo with them. But it's essentially the same thing. So you draw a picture, you select your system. So just like we did with the cars, we're going to select our system. Our system is going to be the whole Atwood machine. So we're going to circle the whole thing. And we're going to choose a positive direction. So looking at this, it says in this figure over here, A in red here has 11 kilograms, and B in blue here is 27. So you have to pick a direction that you think it's going to accelerate. So the heavier side is this B side. So that's the way that I would say it's going to go. So it always goes in the direction of the heavier side. So whatever direction that goes, that direction of the acceleration, that's going to be positive. So anything that's pulling that way, any force that's directed that way in the positive direction is going to be positive. So that force pulling this down, which is the gravity on B, is positive. And then any force that is going against that would be negative. And notice I drew these 2 forces, force of gravity on B and force of gravity on A. They are not the same size. If they were the same size, nothing would happen. The forces would balance and it would not accelerate. And they are not balanced. This B is definitely heavier, so it's going to win the tug of war, and it's going to pull, and it's going to accelerate that way. Okay. The external forces are what we just listed. So the external forces are the gravity forces. There's an internal force here. What do you think the internal force here is that's connecting these 2 blocks? That's the tension. So there's a tension in the rope in that pulley setup, but it's internal. So internal forces we don't worry about. So in the beginning, we're going to solve for the acceleration of the system. And then we're going to, again, like we did in the last problem and the problem before, we'll solve for the whole acceleration, and then we'll break it up into pieces and solve for the internal forces of the system. All right, so we need to develop a force equation. Again, it's just looking at your picture. So what we're going to do this time is we're just going to say the sum of the forces on our blocks. So that's blocks A and B. And that's equal to the forces that you have labeled. And basically, you just put a plus sign between those. So it's going to be, you can put it in any order. It's negative F force of gravity of block A, FGA, plus positive force of gravity on B. So those are the forces that you're adding together to get the net force. The net force is always equal to, according to Newton's second law, mass times acceleration. So this is the mass times the acceleration. Again, what mass is in our system? It's both masses. So you got to make sure you have A and B together. So that is the setup of what you're going to do. And then it just takes, plugging in the numbers and getting a solution. So let me make this a little smaller so it's easier to see. So the force of gravity equation is just M times G. So just to write that at the top here to remind you of that in case you've forgotten. So you're taking the mass of each one and multiplying it by 9.8. So if I'm going to do negative, the force, the mass here is 11, and then it'd be 9.8. And the next one, it would be positive 27 times 9.8. Is equal to 11 plus 27 is 38. So I just added the 2 masses together to get that step. And then A. So we're going to solve for A. If you do all this work, this is like negative 107.8. I'm just showing you all the steps here for the algebra. And then the second, or F gravity of B, force gravity of B is 264.6. and that's equal to the 38A. Again, 38 just came from 11 plus 27. You're going to add those two forces together, and you get something like, oh, I didn't do that on the paper, so let me check. So 264.6 plus a negative 107.8 is, sorry, typed it in wrong, 156.8. So that's 156.8, and it's positive, equals 38A. And again, it's just division at this point. So the math is pretty basic. It's just multiplication or division in most of the math and the solutions. And when you do that, you will get an acceleration of 4.126 meters per second squared. We'll go over more details of like the physical limitations of an Atwood machine in class, but this answer is going to match up with that possibility. Like this is an acceptable acceleration. There are some things that you can't do. Both blocks accelerate in this idea. So like B is accelerating downward at that rate, and A is accelerating upward at that rate. So we've done steps kind of 1 through 4 here. We've solved for the acceleration of the system. Now we're going to separate into individual blocks and then solve for T, which is really Ft, the tension. For this, you can pick either block. It does not make a difference. You just have to draw it correctly, make sure you have the signs right, and then do your work. I'm going to pick block A just because, I don't know, I decided to. So there's block A. If that was our system this time, the forces that are external to the system, we got force of gravity on A, which goes down. And we have the rope itself, the thing that's touching it and pulling it up is the tension. If I asked you which way this thing accelerates, it accelerates up. So up is the positive direction in our picture here. This is, I didn't mention this before, but it's kind of up to you to decide the positive direction. Whatever way you picked in the beginning, that's still the right direction. So for A, up is positive and down is negative. For B, down is positive and up is negative. It just go with the way that it's moving. That's the easiest way to think. So it's just the way the systems move is the positive direction. So tension is going to be positive and gravity is going to be negative. And you're going to come up with your force equation. So we have our sigma F of the forces on A are equal to the tension, which is positive, plus a negative FGA. You always have a plus sign because sigma means add. You basically just put a plus sign between those and you write this equation going across. After you've added the things together, you always set it equal to Newton's second law, or Ma, and make sure you're using the mass that is your system, which is A. So this letter matches up with this letter. Okay. Again, we're just going to do the work. So Ft here, we already know the gravity of A. We did that. We don't have to do it again. That's negative 108 or negative 107.8. And then you set that equal to the mass, which is 11 times A, which is 4.126. You're going to solve for Ft by adding 107 to that side, and you would get Ft is equal to, I got 153.186. It's a force, so it's newtons. So that is the tension. You could check it with the other one, so you could do the same kind of idea with the other one, draw your free body diagram, set up your equation, solve for the tension. You'd get the same number. It's using some different values, but that's okay. You could also check it with, like, you could put this 264 as the force going down and the 153 as the force going up, the difference in those two, and then divide by the mass, and you get the acceleration, which is going to be the same number that we calculated in the first part. So that is essentially what we're doing for Atwood machines, which is not really that different from the other block problems that we just did. In class, I think I'm going to hold off on this one. I'll do this one in class with you guys to see how well we understand it. So we'll try that one later. So, all right, guys, have a great day. I will talk to you later.